So this is section 1.5 in your pre-calculus 20 course. It's pre-calculus 11, McGraw-Hill-Ryerson textbook we're going to use here. So 1.5, guys. 1.5, this concept, this is very, very close to a calculus class right now. So you're taking pre-calculus. This is pre-calculus 20. So we're laying the groundwork for calculus. That's why it's in the name of the course. We're trying to give you skills and trying to teach you and bring you along so that you can understand calculus in grade 12. You've got pre-calculus 30, which is a lot of stuff that is directly related to calculus. But this right here is sort of our first thing in this course that really is very, very calculus. This is at the heart of calculus, really. So this is your first real introduction to calculus concepts, okay? And it's called the Infinite Geometric Series. You may or may not know right now, but we talk about infinity a lot in calculus. That is a huge concept in calculus. And even though infinity is not an actual number, it's a concept. And it means that the number of things will keep increasing forever. Or the list of items is uncountable. There's so many of them. It's more of a concept than it is a number. It's not a number. But when we're talking about an infinite series, what we're talking about is we're talking about adding an uncountable number of numbers, or an infinite number of numbers that follow a certain geometric pattern. And it's actually super, super cool that the concept of infinity helps us understand and solve finite or concrete problems. Okay, so let me take you back a long, long time ago, 5th century BC. Okay, we're talking about a Greek philosopher, Zeno of Elea. He posed 4 problems now known very famously as Zeno's paradoxes. One of them was this, and I'll just read it here. So his paradox of motion states that a person standing in a room cannot walk to the wall. In order to do so, the person would first have to go half the distance, then half the remaining distance, then half of what still remains. This process can always be continued and can never end. Now this is a little mind-bending if you really, really stop and think about it. We all know that if you are walking towards a wall, you can walk all the way over the wall and slap the wall. We know that, right? That's not a big, the baby knows that. But mathematically speaking, if you think about this, you can word it in such a way that the math does not line up with that reality. And I'll say this another way. Okay, let me explain this another way. So if I'm standing right here and I've got the wall at the back of the classroom, in order for me to reach that wall, I first have to go halfway to the wall, right? And so whatever my distance is, let's say I'm about 7 meters from the wall there, I first have to go 3.5 meters, right? That is the distance between me and the wall times 1/2. That's the first step, the first stage of my progress. When I'm at that spot, I start all over again. And I say, okay, now I'm 3.5 meters away from the wall. I have to go at least half the distance to the wall. And so half times 3.5, right? What's that? 1.75? So, you know what I'm saying? And so this process can be repeated forever. And because I will never get an answer of 0, okay, 0 meters from the wall, that will never be the answer when I take an actual distance and multiply it by 0.5, right? You only get 0 when you multiply 0.5 by 0. But since I'm not at the wall, I can't start 0 meters from the wall. So any number, the smallest number that you can think of, like I'm like nose to nose with the wall, okay? This is how close I am to the wall. The smallest distance that you think I can be, if you multiply that by 1/2, it will not equal 0. It never can, okay? So this is concrete, finite math. But Zeno said, hey, listen guys, there's got to be something else. There's got to be something more. There's got to be some point at which half the distance of something super duper small is actually 0. That's what he's saying. He's saying there's got to be some point where if I travel enough of those little tiny distances over and over and over and over and over and over and over again, I actually get to 0. And so there's actually a paradox between finite math, the math that we know of, and reality. So another way to think about this, let's say you have a cookie on the table, and you cut that cookie in half, and you put that half over the side, and somebody eats that. So then you look at that cookie, and you cut it in half again, and then somebody over to the side, and you cut it in half again, and again, and again, and again. There will never be a point where you're all of a sudden you're going to cut nothing. Like if you had the sharpest knife ever, you would get right down to like the molecules and you would divide them. You know, see, there's always something that you can cut in half. Even like an atom, you can cut that in half. You know what I'm saying? So it never actually comes to a point where it disappears. But Zeno says that if we think about this distance as a collection, an infinite collection of very tiny distances, we actually can use that concept of an infinite number of things to calculate a finite number. Crazy, crazy. But it matches reality. So this was kind of the birth of this sort of concept. And this is a big part of calculus. We use this concept in calculus to find limits of things. So if we have something called a convergent geometric series, then we can find a limit or an actual sum if we were to add a theoretical infinite number of those things. Now that's a lot of words, and you have to take some time to digest that, I get it. But let me just talk first briefly about convergent series, okay? So a convergent series, and you're going to want to jot down some notes on this one probably. A convergent series is a series where the numbers basically keep getting smaller, okay? The numbers in the series keep getting smaller. And in a geometric series, right, obviously the numbers... Is it frozen right now? Oh, thanks. Thanks for letting me know. Okay. Well, whatever. We're good. We didn't really need to be unfrozen before, though. So, convergent series. So, if we're talking about a geometric series, right, if r is less than 1, if r is between 0 and 1, yeah, probably between -1 and 1. But if r is a fraction less than 1, not a number bigger than 1, then we're going to have a convergent series. That means all the numbers are going to get smaller and smaller and smaller and smaller, just like me walking towards the wall, right? The distances are getting smaller and smaller. That's a convergent sum. When something converges, it means it comes together. And the idea here is that the sum, it will zero in on a specific sum at the end. So let's read. A series with an infinite number of terms, that's an infinite geometric series, in which the sequence of partial sums approaches a fixed value. That's a little bit wordy, but it basically means that if you were to add these things up, you see at the very end of it, you're adding something that's extremely close to 0, right? So if you're adding something that's virtually 0, you're adding virtually 0, and so that number that you have is virtually going to be unchanged. So there's actual limit, there's an actual sum. Now, the opposite would be a divergent series. Okay, so here's convergent, right? We have this much, then this one, then this one, this one, this one, and at the end you're virtually adding 0, and so we could actually find a sum here. Well, with a divergent series, if the numbers get bigger, okay, and at the end of it, you know what I mean, an infinite number of these, you would basically be adding infinity plus infinity plus infinity, which is like, what? You can't, there's no definite sum there. So divergent means the numbers are getting larger, or they're diverging, going away from each other. They're not converging to anything, they're diverging. So in a convergent series, we can find a sum. A sum is able to be found. Okay, you with me so far? Everyone with me so far? I don't know, maybe Zeno freaked you out there, I'm not sure, but you can look back at it again. So let's talk about some notation here, okay? So you'll see this a lot in calculus. This little sign, do you know what that sign means? Yeah, that's the infinity sign, right on. So we're actually going to be able to find an infinite sum, so a sum of an infinite number of terms. Because theoretically, at the end of the list of all of these numbers that we're adding, we're going to basically be adding virtually 0 at the end. So that means that we're going to grind to a halt, and the sum will be fixed. Okay? Just like me, if I'm nose to nose with the wall, there comes a point where I can say, listen, half of a micron is pretty much, let's just call it 0 now. Okay, right? Half of a nanometer, I'm a nanometer away from the wall. Half of that is, let's just call that 0. So at some point, we're adding 0, and I've now covered the entire distance, and that's my sum, right? 7 meters. Remember, I started 7 meters from the wall. So if I go 3.5 plus 1.75 plus half of that, plus half, plus half, plus half, plus half, half, an infinite number of times, I get to 7. Make sense? Because that's where I started from, 7 meters from the wall. So 3.5 plus 1.75 plus half, an infinite number of times, I'm going to get, in my case, I'm going to get to, 7 meters from the wall. So it's actually, an infinite sum will actually equal a definite or a finite number. And that's the point of this lesson. So what's the formula? Okay. First of all, we have to have a convergent geometric series, and then we can look at a formula that will help us identify the sum. So here it is. I'll just flip this over to the notes. Here's what we're looking at here. The sum of an infinite geometric series where r is between -1 and 1. That means it's like a fraction, okay, like a decimal, less than 1. Positive or negative doesn't matter so much. But if it's got to be, the numbers in the list have to be getting smaller. Then this is the formula. S of infinity, the sum of an infinite number of terms, equals, and it's actually the easiest one of all the formulas that we've learned, right? It's the first term divided by 1 minus r. The first term divided by 1 minus r. So, let's take my example. I am 7 meters from the wall, okay? Now, let's say that I'm picking it up at 3.5 meters. Am I okay with this? So my first distance was 3.5 meters. That's half the distance to the wall. The second one was 1.75. Okay? And then so on, so on. The ratio is 1/2, isn't it? Term 1 is 3.5. So let's see what happens when we stick this together. 3.5 divided by 1 minus 1/2. That's what the formula says. So if I were to add an infinite number of terms that are each multiplied by 1/2 and added together, I get 3.5 divided by 1/2, which is 3.5 times 2 over 1, which is, look at that, 7. So I've covered a full 7 meters if you take that pattern to infinity. Okay? I know this is a little mind-bending, okay? This is out of the box, okay? This is out of the box. I get it. Mr. Maxwell, I still don't get how we can add an infinite number of things because I don't even know how many things is an infinite number of things. I get it. The pattern is increasing forever, and at some point, half of a very small number is 0. So we're actually grinding to a halt, and that sum can be found. Now, this is an approximate sum, right? This is still our best guess because we haven't added up an infinite number of things. That would take us an infinite amount of time to add up an infinite amount of things. But this is the pattern that we see. Okay, questions? Do I dare ask for questions here? Any questions? You all look like you're about to cry. Is that true? Is this a bad thing? Are you going to cry? No? Okay. Got some smiles. Still some tears. Okay. Anybody else? No. Any questions? Any questions from the back? Things I might have missed? No? No? Okay. You guys, you're good back there? Okay. Okay. All right. A quick example. Determine whether each infinite geometric series converges or diverges. So let's just take a quick look and see if we can find out what R is, and also just take a look and see if these numbers seem to be sort of getting smaller and smaller, and if indeed they are geometric. Now, if it's an arithmetic series, this doesn't work, guys. Okay? If it's arithmetic, it does not work. Because let's say we had 10, 5, 0, -5, -10, and so on, and we keep adding a common difference of -5, way down the road, I'm going to have like -1 trillion, right? And so if you keep adding larger and larger negative numbers, you're not going to zero into like a certain sum. Remember, at the end of the row here, if we're adding something very close to 0, then we can find a sum. So arithmetic doesn't work, and divergent geometric doesn't work. So 1, 1/5, 1/25. Do these numbers appear to be getting smaller? Yes. 1/5 divided by 1 is 1/5. Is 1/5 in between -1 and +1? Is that true? Yes, it is. So the R is between -1 and +1. This is convergent. B. Do these numbers appear to be getting smaller and smaller, approaching 0 in a geometric sense? Nope. R is 2. Is 2 between -1 and 1? No. This is divergent. Got it? R has to be like a fraction. Positive or minus, a fraction between -1 and 1. Okay, that was easy. That was maybe too easy. Okay, there is an example here expressing a decimal. I don't think you guys need to do this. I do this with you in calculus a little. Well, actually, that's not really. I don't know. I don't think I'm going to make you do this right now. So this type of question. So we'll see though. I might show you tomorrow. I don't know. Okay, so here's the key ideas. Please take a moment to look at those, read through those. If there's anything you don't understand, let me know. I'll get together your assignment here. Okay, there's some suggested questions for 1.5. I think that would be very good practice for you. Okay, so here's just a quick shot of some of those questions if you get stuck at home without a textbook. And if you get through this, please take a chance to do an extend question. Okay, those ones are a little bit more challenging. So if you're getting through this stuff and it's like, oh, I got a handle on this, it's pretty easy, do an extend question. It'd be really, really good for you to sharpen up your skills there. Okay? All right.